Hey guys, here's a video on curve sketching in case you missed class today or slept through my super exciting lesson. Okay, so curve sketching, and this is for B1. Everything you need to know, almost. Okay, so I'm just going to do pretty much exactly what we did in class today, just to recap it. So we're starting with a function. We're just going to do polynomials right now. So let's pick a polynomial function. I'm going to pick x cubed minus 3x. That's the one we did in class, so you can see the note on it if you want. And I picked it because it's easy to factor, so we don't have to get too crazy. Okay, so here is our original function. F of x equals x cubed minus 3x. We know it's a polynomial function. And we also know some stuff that we learned in advanced functions. So step 1 stuff, let's just kind of sketch it out because we know what it looks like. We know it's a degree 3 because that's the highest exponent, and so therefore it's an odd degree function, and it's got a positive leading coefficient. And what that means is degree 3, so if it's an odd degree and a positive leading coefficient, we know it's going to end up in going from Q1 to Q3. So we don't know exactly what the graph looks like, but we know maybe something like so. So we learned that from advanced functions. So remember, if it's an even degree, then it's going to either end up in Q2 and Q1. So even degree would be like that, or it could be the bottom two quadrants, and then odd degree would always be 1 and 3 or 2 and 4, depending on the leading coefficient. Okay, so you can review that if you want to. There's probably some YouTube videos on it. Alright, so that's our first step. We figure out kind of our end conditions. Let's call them that. End conditions. It's not a requirement, so if you totally forget how to do that, no worries, but we know our end conditions are Q1, Q3. And that's what we learned in advanced functions. Okay, moving on. Next thing we want to do is we want to figure out our intercepts. So intercepts are our next thing we want to figure out. So we're trying to draw the most accurate sketch of x cubed minus 3x in the world. Okay, so we're going to get our intercepts. So we want our x and our y. So let's start with our y-intercept. So we know when we're trying to find the y-intercept, x will be equal to 0. So let's find f of 0. So we just sub 0 in for x, and we get 0. So therefore our y-intercept is 0, 0. And then let's find our x-intercepts, which is when we set y equal to 0. So sometimes there's 1, 2, these ones are trickier to get. So we actually set f of x equal to 0, and we get 0 equals x cubed minus 3x, which we can't just directly solve. So usually we'll have to do some factoring. So I'm going to factor out, I can see that they both have an x, so I'm going to common factor out an x. Okay, then I would see if I could factor this bracket any farther. X squared minus 3, it's kind of like a difference of squares, but that 3 is kind of annoying, so I think I'm just going to go ahead and solve it. So I'm just going to separate these two terms, and I'm going to say x is equal to 0 and x squared minus 3 is equal to 0. So here's one root at 0. And then my other root, I just have to solve this equation. So I can actually just bring the negative 3 to the other side. So we got x squared equals 3. And then to get rid of a squared, I think I'll just square root both sides. And remember, when we square root something, our answer could be positive or negative. So my answer would be plus or minus root 3, which I'll just write as 1.73 and negative 1.73. So those are, I've got 3 roots. So I found all my intercepts. So I've got 0, 0, 1.730, and negative 1.730. So I've just found 3 points. I got my x-intercept and my y-intercept, and 2 more x-intercepts. Okay, so my graph's coming together. I kind of know my end conditions. I know where they're going to cross the x and y axis. Now we're just going to use a little bit of calculus to get the rest of our information. So end conditions, intercepts. Next we're going to use the first derivative, we're calling it, which is the derivative. But we're going to learn how to take like multiple derivatives. So we're going to use the first derivative to tell us some stuff. Okay, so let's find the derivative. So f prime of x equals, we just have to use our power rule. So x cubed becomes 3x squared, and 3x is just minus 3. So there's our first derivative. F prime of x equals this. So when we're sketching our graph, we know it's like something like this. Things that we couldn't do in advanced functions are we couldn't pinpoint these locations here. And those locations are so important to make our graph accurate. So let's call this the local max, and we'll call this guy the local min. Local maximum, local minimum. We're calling them local because technically the graph keeps going. So the max is just going to not be right there, but locally it is. They're sometimes also called your extreme values or extrema. Sometimes they're referred to as that. And those occur when we have a slope of 0. So if you draw some tangent lines on your graph, you can see, oh, I got a positive slope, ooh, a 0 slope at my max. Then it's going down, 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 0, up, up, up. So if I'm looking at, remember the derivative actually tells us the slope of our function? So I'm going to use that to figure out my max and min. So I know if I set my derivative equal to 0, that's where the function will equal 0. It will have a 0 slope. And that's right at my max and right at my min. So I should get two values solving this equation. So we sometimes call this the first derivative test. So the first derivative test, we can use the derivative to find out where the max and mins are. So to find out where our derivative equals 0. So it will tell us if there are any max and mins. And it can also just tell us the values of our slope. So it can tell us like these sections has an increasing slope, whereas this section has a decreasing slope. A negative, or sorry, I shouldn't say decreasing. I mean, that's not what I mean. I mean, this has a positive, the red sections have a positive slope, and the green section has a negative slope. Sorry. Okay. So let's solve this equation. So I think it'd be easier if we just bring the 3 over, the negative 3, or add 3 to both sides, however you think of it. So 3 equals 3x squared. I'm going to divide both sides by 3. So 1 equals x squared. Then I'm going to square root both sides. And I have to have a plus or minus sign when I square root. So my answer is x is going to equal 1 and x is going to equal negative 1. So that'll be my max and my min. And then I'm just going to make a little table here because I want to highlight what exactly is going on in this graph. So I know I'm going to have a max and a min at negative 1 and 1. I'm going to have an intercept at 0. But I just want to kind of draw out what's going on with my graph. So I'm going to do what's happening when x is less than negative 1. What's happening when x is negative 1. What's happening when x is between negative 1 and 1? What's happening when x is 1? And what's happening when x is greater than 1? So I'm just making this table, just think of it like my x-axis, this table is, and I'm just sketching out what my graph's going to look like. So these values here, 1 and negative 1, are pretty special values. They're our max and mins. So we're going to call these our critical numbers, or critical points. They're so critical. They give us some more specific graph than we could have got before. So let's figure out what the y values are there. So we already know the derivative of them is 0, so I'm just gonna draw that out. So when we take the derivative at negative 1, so if you subbed negative 1 into the equation, negative 1 squared is 1, times 3 is 3, minus 3 is 0. So we know that the derivative equals 0. So therefore it's going to produce a max or a min. And let's just find the y-coordinate so we know the exact location. So if we just do f of -1, so go back to your original function. Your original function was x cubed minus 3x. So if we plug that into our original function, we're going to get -1 plus 3, so 2. So that means we're going to have a max or a min at -1, 2. Cool. Let's go to our other max or min. So we know if we took the derivative at that point, it would equal 0, which tells us we have a max or a min. And then if we go back to our original function and plug in 1 to the power of 3 minus 3 times 1, we will get 1 minus 3, so -2. So we know we're going to have a max or a min at 1, -2. So yeah, I'm just going to highlight these because these are our critical points. And now we're just going to map out, even if we didn't know our thing went like this, like what if we're like, oh, what if it goes like this way? We can't remember advanced functions. So we can use derivatives to help us. So we can just like say, okay, what if x is less than -1? So pick a number that's less than -1. Let's test. Let's use a test value, -2. I just picked any number that's less than -1. So I'm just going to test this out. So I'm going to use my first derivative, which is 3x squared minus 3. So that's my first derivative. And I'm going to plug in the value -2. So 3 times -2 squared minus 3 is equal to 3 times 4 minus 3, 12 minus 3, 9. So that is a positive value. Which, remember the first derivative tells us the slope of a line of our function? So if it's telling us our slope is positive, our graph must be going up to the right. Here we know our slope is actually 0, so our graph will be flat in this section. Let's check out the interval between -1 and 1. So test any value. Let's say we tested 0 out. So we're going to sub 0 into our derivative. So our derivative equation was 3x squared minus 3. For subbing 0 in, that's just going to equal -3, I believe. So if we have a negative value, that's our slope. So that means we have a negative slope. Negative slope. So it'll be going down to the right. Here's a critical point. We already know the slope is 0 here, so we're going straight across. And then when x is bigger than 1, pick a value. So you could pick x as 400 if you feel like doing that math, or you could just pick 2. Do the derivative. So f prime of 2 is equal to, remember our derivative is 3x squared minus 3, so 3x squared minus 3. 3 times 4 minus 3, and 12 minus 3 is 9. So it's a positive value. And remember, a positive value means positive slope, so we're going up to the right. So this, like these little calculations here just kind of tell us positive, 0, negative, 0, positive. It's telling us the direction our graph is going. Super helpful. So the first derivative can tell us about our slopes. Sorry. So the first derivative has told us going positive, 0, negative, 0, positive. So it's telling us what's happening with the slope of our line. And we also know, based on our slopes, when you go from positive to negative, so if you go up, down, you're creating a peak. So this value here must be a local max. That's good to know. And then when we go from negative to positive, negative, positive, not so much like a V, but anyways, that creates a little minimum, a local minimum. So there you go. And these are just local max and mins because they're not the absolute maximum of the graph. Okay, so it's important to know that a maximum is created when you go from positive to negative. So a positive slope to a negative slope gives you a max point. And then when you go the other way, a negative slope to a positive slope will create a minimum. Minimum, maximum. Okay, cool. So the first derivative just helped us figure out max, mins, what our graph's doing. Okay, there's some more information that we can collect. Like a never-ending amount of information. Okay, so the other piece of information is something called concavity. So this is important, concavity. We're going to figure out the concavity of our graph, meaning we already kind of know that our graph looks like this, but I'm just going to point out this section of the graph, if we split it here-ish, this section is concave down, it's called. And this section of the graph is called concave up. So a way to think about that is if you draw the tangent lines of your slope, notice all of the tangent lines are above your function. So they're all on top of the line. And then when we start to go concave up, we would draw our tangent lines underneath our graph. So there's a point here where it changes from like concave down to concave up. And that special point is called the point of inflection. Okay, so knowing all of this stuff, there's this thing called the second derivative that can tell us if our graph is concave up or down and where the point of inflection is. So the second derivative, which could be like f double prime of x, is when we take the derivative of the derivative. So our graph, we had an original function that was x cubed minus 3x. Then we took the first derivative of that, which was 3x squared minus 3. Then here's what we want to do next. We want to take the second derivative, f double prime of x. So we just take the derivative of the first derivative. So 2 times 3 would be 6, x minus nothing. So our second derivative is f double prime of x equals 6x. And this is special because it's going to give us another critical value, and this value is the point of inflection. So when we set the second derivative equal to 0, we get a point of inflection, possibly. So it just depends on the situation. Okay, so let's just sketch out what that looks like. Actually, let me tell you some info first. So if our first derivative is equal to 0, remember that will produce a max or a min. And then if our second derivative is greater than 0, our graph is actually going to be concave up. And therefore, that means our first derivative would have produced a local min, a local minimum. So it's kind of crazy, but you know if your first derivative is 0, we got a max or a min. So we could just take the second derivative, and if the second derivative is greater than 0, then we've got a minimum because we got a concave up situation. So let's test that out with our own graph. So the graph that we were just doing, x cubed minus 3x, this guy. So we found our second derivative was 6x. So let's set that equal to 0 just to see where our possible point of inflection is. So 0 equals 6x, therefore x would be equal to 0. So we have a possible point of inflection at x equals 0. So we already found, like so far, let's just take a sec here and graph what we know. We know we have roots at 0, 2, 3, 1, 2. I'm just going to sketch a quick graph because we're like learning a lot right now. It's like a lot. So we had roots at 0, positive 1.7 something, and negative 1.7 something. So those were our roots, and our y-intercept was 0. Okay, that was our first step. Then we found we had a max. Just going to scroll up for a sec. We had a max at negative 1, 2, and a minimum at 1, negative 2. So let's put those on our graph. So a max at -1, 2, and a min at 1, -2. Okay, so that's our local max and min. Those are our three roots. So let's check how the second derivative tells us stuff. Okay, so the first derivative was equal to 0 at, whoops, sorry. Okay, the first derivative was equal to 0. First derivative was equal to 0 at -1. That's when we found our maximum here, our local max. So let's test out what the second derivative would be at -1. So we just plug -1 in for x, and we get -6. So that must mean we can add this to our information. If f prime of x is equal to 0 and f double prime of x is less than 0, then we must have a local max and our graph will be concave down. Because, okay, so we just found we have a local max here at -1 because our first derivative equaled 0. And then when we try our second derivative at that point, it's a negative number. So therefore, we know our graph is actually concave down. And therefore, this does produce a max. Because you know, if you're like, oh, is that a max or a min? So because we know our second derivative makes it concave down, we know we have to have a maximum. So let's test for the next one. So say we plugged in f prime of 1. For our first derivative, we know that that equals 0. So we were like, oh my gosh, is that a max or a min? So then we plug it into our second derivative. 6 times 1 equals 6. So since that's a positive value, positive, then we know our graph must be concave up, and this must produce a minimum. So a minimum. Okay, so that's what our final graph looks like. So we've got a local max, we've got a local min here. We've got concave up section happening when x is less than 0. We've got concave down. When x is greater than 0, we've got concave up. So another thing we want to add is when our graph goes from concave down, when x is less than 0, make a table on the fly. Then when x is greater than 0, it goes concave up. So it's just the shape of the graph. It goes from concave down to concave up. We've got right at x equals 0, we have a point of inflection. So to get a point of inflection, your graph has to go from concave down to concave up, or the reverse, concave up to concave down. And the point of inflection is kind of where it turns. So it's going like, I'm just going to use a highlighter, it's going like concave up this whole time, and then boom, it switches to concave down. I just reversed that. I'm an idiot. Okay, so it's going to concave down the whole time, concave down, and then boom, point of inflection, concave up. So this is our point of inflection. Point of inflection, where it turns from concave down to concave up. And our point of inflection happened when our second derivative was equal to 0. So our second derivative was 6x, so we set that equal to 0. So we found that at x equals 0, we have a point of inflection. And if we want to know what our y value is, we go back to our original function, x cubed minus 3x, and we sub in 0. So it's 0. So at the point 0, 0, we've got a point of inflection. Whew! And that is a lot of stuff. But that's like almost everything you need to know about curve sketching in 25 minutes. And then the homework I gave for tonight was, I said you should be able to sketch this graph. F of x equals x cubed plus 6x squared plus 9x. So everyone was going to try to do that, I hope, or during class. And I said steps you should take are first, figure out the end conditions if you remember. If you don't, it's not a big deal. You can figure them out later. So degree 3 positive leading coefficient, what happens? Second step, determine your x and y intercepts. Determine x and y intercepts. And third step, do some critical point stuff. So you can use your first derivative equal to 0 to help you find your local max and mins. And you can check the intervals before and after. So when the when the interval is less than whatever your max is, and to set yourself up so you're like x is less than whatever, and then x is equal to your critical point, and then x is between this and this. So just try to figure out what's going on either side of your critical points. You can figure out concavity and points of inflection using the second derivative. So that can tell you your point of inflection. And with the first derivative, you can learn about increasing, decreasing, positive, negative slopes. And with the second derivative, you can learn about concavity of your graph. So yeah, try to figure all that out using this polynomial. And then tomorrow's class, we're going to try to go outside.